All right, shall we get started?
I think so. It's past 2:30, yeah.
Okay, so welcome back, everyone. Let me just quickly share my screen just for a recap of where we are in the tutorial. So we covered part 1 and part 2 in terms of the introduction and the DeepONet. And now we're moving to part 3 and part 4. So heading down the black diamond slopes might not be the best idea since we just had lunch. But thankfully, we have Jacob that has been doing a fantastic job in explaining even the most difficult topics very clearly. So I'm just going to hand it over to him to talk about Fourier neural operators and more specifically the Fourier neural operators. So let me stop sharing, and Jacob, you can take over.
Thank you, Paris. Okay, so now at part 3. In part 2, we talked about the DeepONets, which is proposed operator learning architecture that we came across. And now we're going to discuss an alternate way to formulate an operator learning architecture. The Fourier neural operator is built off this idea of the neural operator. This is an idea that came out of Caltech. Again, both of this and the DeepONets are really very recent architectures that have come out in the past couple of years. So for the DeepONet, we kind of motivated its construction by this result of Chen and Chen in 1995, where they were able to come up with this universal architecture that was provably able to approximate any kind of continuous operator between two spaces. And then we used neural networks for the two components of that architecture. We're effectively approximating some finite dimensional subspace that we hope is very, very close to the true image of our operator. But in this section, we're going to take a bit of a different approach and kind of start from the point of what happens in deep learning for normal finite dimensional maps. And so as many people might be familiar with, the simplest kind of neural network architecture that you would learn about getting into deep learning is this idea that we're going to iteratively compose linear and nonlinear mappings. And this is the deep in deep learning, is that we do this a bunch of times. We get a long architecture of linear pointwise nonlinearity, linear pointwise nonlinearity, the neurons and the connections between the neurons, literally. And that this kind of architecture ends up being very, very expressive, very powerful, and relatively easy to train. And as we know, it's been proved many times over in a few different ways that this is theoretically universal from an approximation theoretic point of view. With a deep enough network or a wide enough network, some combination thereof, we will be able to approximate any continuous map between finite dimensional spaces. So we might be motivated to say, we want to form a really flexible class of parameterized operators to learn the correspondence between input function and output function. Why don't we try doing the same thing? And the most immediate application of this is, well, we could apply it just to the output space of the first function. Let's consider the case where the domains of the input and the output function coincide, just to say calligraphic x is equal to calligraphic y. And we could literally just use a multi-layer perceptron standard neural network on the target space of the input function. And this does give a well-defined operator between a space of input functions to the space of output functions when calligraphic x and y are the same. But we can pretty quickly see that this is not going to be a rich enough class of functions. And it's somewhat clear to see why this is the case. That's because this is only operating pointwise on the outputs of the function. So, we used an architecture that was from the finite dimensional case, just acting pointwise on a target space. So this is exactly what this is going to do. This doesn't take into account any information about the curve at all. It just looks at a particular output point and it transforms that output space into another space. So for example, if I had two curves that intersected at a point, like I say I have one line, this is one input curve, I have another input curve this way, and they cross at an x, at the point that they intersect, where those two curves get mapped to, will also have to intersect at that point, because this is a purely pointwise transformation. So it doesn't take into account any global information about the curve at all. And so surely this we shouldn't expect that this is going to be powerful enough to approximate operators that otherwise might be looking at the entire curve, and it might send two curves that intersect to two curves that don't intersect. That's not going to be possible with this kind of pointwise transformation. So we need to add some other ingredient into this linear, nonlinear layered composition, which we will still try to do because we know in kind of standard machine learning, this does work well. So the question is, what is the appropriate analogy of a layered nonlinear linear architecture for operators? And so one thing that you might immediately notice is that on function spaces, there's a much larger class of linear transformations than just linear transformations acting on the output of these functions, which is to say pointwise operations. We might consider those purely local linear transformations of functions because they only depend on the value at that one point. But we have much larger classes of linear transformations. For example, if we take a continuous kernel on the input location space of the input function, again, recall that an input function u is going to be a function from, let's say, calligraphic x to some r to the du. We can take a kernel on the domain of the input function u and convolve u with it. So this is sometimes referred to as an integral kernel transformation. And you can see immediately this does give a well-defined linear map on the space of continuous functions as long as this kernel is continuous. Because I could, give a u1 plus u2 here. Integrals are linear, so this will split into two pieces. Scalars pop out of integrals, and this is a well-defined linear map. But for kernels that aren't, delta functions, I can't represent this as a pointwise transformation with some matrix. And this is the kind of transformation that only appears when we look at function spaces this way. This isn't something that we really see in finite-dimensional spaces, at least not in this formulation. So surely we should include this extra structure that we have of linear transformations on function spaces in our layered architecture that we want to propose if we have any hope of it being expressive enough to capture all the sorts of behavior of mappings from input functions to output functions. Interestingly, there's actually another motivation for using this kind of kernel integral transformation, and that comes from the theory of linear PDEs. So consider some kind of linear partial differential equation. L here is some linear differential operator, some mix of partial time derivatives, maybe some partial space derivatives, but that acts linearly on this input function u, and it should equal some other function f. You can think of this as maybe the Laplace equation or maybe the heat equation. And the operator learning problem for a PDE like this would be, we effectively want to learn the inverse of this differential operator, maybe subject to some boundary conditions for it to be well-defined. So if you give us some right-hand side of this, we apply the formal inverse of our linear operator to it, and we get the solution operator. There are cases where there's something called a Green's function, and the Green's function will allow us to find this answer by convolving it with the right-hand side. So we actually know for a fact that there are operators that we might be interested in learning that have exactly this form and nothing else. So we really have very strong motivation to include this as a module in our layered architecture if we want to be doing learning between function spaces. Are there any questions here? Okay, so this motivates the architecture of the so-called neural operator. And the idea is we're more or less going to emulate exactly what happens with normal multi-layer perceptrons or standard feed-forward neural network, but we're going to include this extra kind of linear transformation that we're allowed to make on spaces of functions, with the hope that then this gives sufficient expressive power to model any kind of operator that we would want. What we talked about in the beginning was if we ignore this part and just look at this, it's not going to be enough. But by including this integral transformation, we're kind of tapping in to the additional structure of the function spaces and the kinds of transformations, continuous transformations we can make on them. We still will allow sigma to be a pointwise nonlinearity. You certainly could come up with crazy complicated nonlinear transformations of functions, but we actually will stick with the very simple form for the nonlinear part, especially since we're going to compose multiple layers of this over and over again, similar in spirit of deep learning. What's interesting about this kind of architecture is that whatever measurement points you have of your input function, this part is being applied pointwise to them. So that part doesn't care what those are. But there are many ways to compute this integral, which we'll talk about in the next few slides, many of them of which will accept different measurement schemes you might have for the function that you're putting in here. This kernel is something that we're going to learn or design ourselves, so we'll be allowed to evaluate it anywhere. We'll only have access to this at some measurement locations, but because we're writing this as an integral, it will be very flexible with respect to where those locations are. And in my opinion, this is a trick for any kind of function space to function space learning that's very powerful, and it most of the time ends up looking like some kind of integral. We'll talk about that a bit more later in this talk, and then also in part 4. Does anyone have any questions on this overall architecture? Okay, so we formulated this on paper, very nice, but now we're going to put it into a computer. We have a finite collection of measurements. We actually need to decide how we're going to compute this integral and make some choices. So the first option results in what's called the graph neural operator, which was the first version of this architecture that appeared, presented. And the idea is that we'll use a Monte Carlo approximation of the integral. So we'll say we have a couple of measurement points. They were maybe chosen uniformly at random from the domain, maybe not, but we'll pretend that they were. And so we'll just take a straightforward average then of the integrand here. Is the simplest kind of approximation of an integral we could possibly do. If the kernel that we have is somewhat localized, which is to say that it decays off its diagonal. By the diagonal, I mean if you put the same point into the kernel twice, then we can only, that would mean that the values of this are very, very small unless x and zi are close together. And so how you end up at the graph neural operator is, let's say this kernel only has support for fixed x in a ball of some small radius around x. I can look at all of the measurement points that I have, and I can form an edge to those other measurement points that are close enough. Then you can implement this procedure for approximating the integral with a message passing algorithm on this graph that I formed based on the kernel. What's nice about doing this is that if I get a new measurement point, or I lose a measurement point, I throw it into the graph, I make a new edge, I take away the edge, and I still run the same thing. Of course, these might give you ever so slightly different answers, but the idea, and again, the overarching philosophy of this way of approaching the problem, is that all of these different discretizations are approximating the same thing. The more measurement points I have, the more accurate this will be, but it is still well-defined with respect to different collections of measurement points, and it doesn't change the parameters that I've used to learn this kernel function. This might be somewhat expensive if we have a large number of measurement points, because we're going to need to effectively compute this big kernel matrix of all the points with each other, especially if it isn't super localized. But then there's a whole bag of tricks for computing kernel matrices like this. You can use Nystrom or low rank approximations. There's an extension of the original graph neural operator paper to kind of multi-pole discretizations where you kind of zoom out on varying scales to approximate the behavior overall. And lots of other tricks in the literature coming from different areas, but anytime you want to approximate some big kernel matrix between a lot of points, you do have options if that becomes large, because the naive scaling here is going to be quadratic in the number of points that you have. So a lot of measurement points might become infeasible at some point, but you can use random feature expansions, low rank approximations. You have options if you want to do it this way. So there's another option to compute this integral kernel transformation that will lead us to the Fourier neural operator. And it's based on the observation that if we restrict ourselves to a stationary kernel, we have the beautiful results about convolutions and Fourier transforms, which is that the Fourier transform takes integral convolutions to pointwise multiplications in the frequency domain. And so because of this, we don't even have to learn this kernel directly. We can just learn its Fourier transform. And what we'll do is we'll learn its components in the frequency domain. This just becomes a standard multiplication, very, very efficient to implement. And then we'll take the inverse Fourier transform to get the answer of this full transformation. So we'll just learn the Fourier transform of K directly in frequency space. We'll just learn, the coefficients of its Fourier modes. And then if our measurement points are nice enough, we'll discuss what that means. We can use the fast Fourier transform to do, the moving to the frequency domain and back, which is really, really fast, as the name suggests. So this is a very efficient way to implement this kernel transform, and it ends up actually working really well and being pretty powerful. So as you said, they're very fast. You don't have to worry about these approximations for computing the kernel matrix like you do in the graph version. What's also really nice is if you end up having measurements that are sampled at a more fine resolution, you still can take the Fourier transform. Now you have access to some higher modes, but you don't necessarily need to use them. You can still use exactly the same kernel that you had from before, and then recover a finer grid than you trained on. In the sense, you can do one-shot super resolution, which is a heavily advertised feature of this method, which is very cool. And also, again, compared to the graph neural operator version, there's no computational cost for not having a kernel which is concentrated along its diagonal. In the graph neural operator version, if the kernel sort of sees everything in the domain and doesn't start getting small outside of neighborhoods of points, that really increases the computation time. But because we're using the Fourier transform, these sort of global relationships don't incur any sort of extra cost. And so here's a diagram of how one of these layers would work for the Fourier case. We'll have the input function to this layer. We'll take its Fourier transform. We'll hit it with some matrix of frequencies, which represents the Fourier transform of the kernel. And then we'll undo the Fourier transform with the inverse transform to get back to the physical space. Meanwhile, we have this pointwise linear transformation that's acting on the input. And in this sense, this actually looks a lot like a residual sort of architecture, like some kind of ResNet, where you're sort of going through frequency space for your nonlinear component inside of the pointwise nonlinearity, of course. And as many of you might be familiar with, these kinds of architectures end up being very, very powerful. So people who have worked on this architecture do give some universality results again, similar to the DeepONet. The method of proof is a bit different. The statement ultimately looks a bit different as well. So because we're using the Fourier transform, there is some subtlety about being on periodic domains here if we want to have, countable spectra. These papers do give some details about the existence of periodic extensions, extensions of your input function to periodic domains. So in theory, it always is, under reasonable assumptions possible to do this. And also the approximation theoretic results are given in terms of norms on Sobolev spaces. Things become very nice. For those of you who might not be familiar, Sobolev spaces are spaces of functions where you know that they have derivatives which exist in a suitable sense, and that those derivatives are sufficiently well behaved and integrable. So the first Sobolev space would be like a function that has a first derivative and its first derivative is in L2. In these function spaces, you can say things about how the Fourier transforms of these functions are behaved. And it means that they decay at certain rates. This makes a lot of things very easy. So for the Fourier neural operators, a lot of the results are stated in terms of norms on these function spaces, because it's what the theory kind of allows you to do more easily. But the spirit of the result is more or less the same. We're restricting ourselves to compact subsets because it makes these theorems easier to prove, though you can generalize them to measurable operators instead by the usual tricks of approximating them from the inside with compact things. And additionally, there are other universality results for the broader class of neural operators, not necessarily using the Fourier transform. And in this paper, actually, they give the results in terms of some more general norms on the function spaces. These proofs are somewhat involved, but main point of this being that we started by being inspired from deep learning and saying, let's have a layered architecture, which is linear, nonlinear, alternating. We wanted to use this kernel because it gave us a richer class of transformations that would exist on function spaces. And ultimately, this idea worked. It is sufficiently powerful to approximate any kind of operator that we would potentially be interested in under reasonable assumptions. There's one question. So the learned kernel is positive definite. So the question was, aren't there some specific constraints that also need to be imposed on the Fourier transform of K so the learned kernel is positive definite? I don't think that there is a requirement in general that that kernel be positive definite. I'm not sure if there's somewhere that states otherwise, but what I have seen so far does not put that requirement. If you did want your kernel to be positive definite, then you likely would need to make some assumptions. But I don't think in general that that is required. Any other questions? Okay, so now just some comments on organizing training data sets for Fourier neural operators. Typically, if we're going to be using the fast Fourier transform, we're going to want our measurement locations for the input and the output to be on somewhat regular grids. So in this case, a single training example would be this grid of input function locations, the associated function values there, and then we have the grid of output locations and the associated function values there. And an interesting thing about this architecture is because we're using the inverse, we're taking a Fourier transform and then taking the inverse Fourier transform, a single forward pass of the model is always going to give you the full grid. You don't have to query the full grid, implementation wise, and we'll see, examples of how this works in code coming up. But computing the output of the model will always compute the full grid for you. But as I referred to before, you can train on a single resolution and then make your mesh finer or less fine, and the model will still run and the parameters won't change at all. Another question here. Oh, this is a comment saying that the Fourier kernel is positive definite, so Mercer's theorem can be used. So that's for the kernel of the Fourier transform itself. I think I want to clarify something, that there's the kernel that is involved when we take the Fourier transform of something, but this is not necessarily a Fourier kernel itself. This is an arbitrary kernel that we would like to learn to represent a linear transformation of this part of the architecture. Okay, so this is just an application highlight. So this was from NVIDIA, I believe. Oops. And this was for modeling climate simulation for predicting the path of a hurricane using, a grid of data over the surface of the Earth. And it's work. We do see some pretty, impressive prediction. They have here, you'll see as the globe kind of swings around, it'll compare it to the NOAA forecast. We see their simulation is in the purple kind of contours, and the forecast that the I guess government agency otherwise uses is in the white cone, and they end up getting pretty good. I guess the ground truth is then the kind of colors that you see there. Try watching that one more time. But this is starting to be deployed for real applications and is giving, some pretty cool performance. So we do expect to see this kind of model and other similar models to really be increasingly used for real applications. Just the minor drawback is that the two grids that we use for the inputs and the outputs do need to be the same because we're going through the Fourier transform, but the resolutions of those two can change from example to example. There are extensions of the fast Fourier transform where you don't have to be on a regular grid. Most available implementations of it so far do require you to be on a regular grid, but there are some that are coming out that let you change to more complicated geometries. The other drawback, and we'll see some examples of this in part 4, is that it does not always have the best robustness against noisy corruptions of the input. And that is also because we're using the Fourier transform for this case. Okay, so that concludes the description of the model. Next up, we'll show some implementations of this in JAX. And then we'll move on to part 4, where we'll describe a new model that we have been working on and some interesting applications of operator learning methods in general. Are there any questions, I guess, before we move on? I can stop sharing here.
Okay, so I will start. There are any questions, and then you can address them. Okay, so the Fourier neural operators. Okay, so this is a general sketch of the Fourier neural operator that's modified for purposes of notational consistency. So in the paper, you will see this is denoted by A, and the input and the output is denoted by U. So because before we denoted the input by U and the output by S, we changed it such that is consistent. So again, this is to have the same setup. So we have some X inputs and some Y output query locations. We have some input and output function pairs, right? And we want to learn an operator using them, right? So as we said, the Fourier neural operator is an iterative architecture, like V0, V1 to V big T, right? And then this can be split in three parts, right? The V0, which is essentially something that lifts the last dimension, like the channel dimension, and then there is iteratively applying this neural operator layers. And the last dimension essentially projects back the channel dimension to the dimension of your output, right? So the first and the third part, they're doing by some local transformation. For example, some shallow fully connected layer. They are using also convolutional layers, but anyway, we will use fully connected layers here. Okay, so let's see how the step 2 works. Okay, so step 2 is we define this V tap plus 1, which is essentially what Jacob described, which is this linear layer with a nonlinearity. And K can be defined as some integral operator, which then we take the Fourier transform of that, we do the Fourier trick. So what I'm trying to explain here is when we go to the implementation and we will see how the spectral convolution is constructed, you will see something that's not essentially familiar. There is some matrix vector multiplications. And so I'm trying to motivate why these matrix vector multiplications are why is this implemented like that in the first place? And this comes essentially from the math, right? From properties of the Fourier transform. So thus far, this is what Jacob described. You have this Fourier transform of kappa, then Fourier transform of V, and then this kappa is essentially this is parameterized by, this is called R phi, which is parameterized by some complex parameters, right? So if you go to your paper and section 3 and 4, you will see that you can actually consider some properties of the fast Fourier transform, and then this essentially reduces to some matrix vector multiplications with the corners of R, right? So this is actually a very, very cool trick. You can check that out in their paper. I highly recommend it. So now what are we going to do next is we will again explain the problem that we are trying to solve, which is again the same flow through porous medium. Okay, so the setup is exactly the same as it was before. There is nothing different, right? There is again the Darcy law, again the same boundary condition, the same dimensionality, the input and the output domain coincide. There are scalar fields, right? So exactly the same. Everything is exactly the same. Okay, so for this particular tutorial, we will need a deeper introduction to stacks, right? So let's start by importing these necessary libraries. Okay, okay, so this is some. Now, as we talked before, you have this R matrix, which is complex. It's complex value, and this is trainable, right? You learn these parameters from your data. That means that you need to go to change some parts of the up-down optimizer to properly use it. Okay, so this is how the optimization is done, how the update step is done, the gradient-based optimization. And when you have like complex parameters, then you can have these Wirtingen derivatives, and they look like that. Okay, in the case of JAX, when you take the derivatives of the loss function with respect to these complex parameters, you get this derivative where is this minus here, right? And obviously we don't want this minus here, because minus here, no, this will probably don't work as it was supposed to. So what we need to do is take the conjugate of that, where's the plus, right? So this is the first thing that we need to do. The second thing that we need to do is the atom optimizer computes the squared norm of a gradient by squaring its elements, right? This, in the complex case, will not give us the norm that we are supposed to get, right? It will only works for real parameters, right? Real gradients. So, okay, so then what we can do is go to the optimizers, the stacks optimizer source code, take this complex atom, right? And then take the conjugate here, and then instead of having g squared right here, you just need to multiply the conjugate g by g, right? And then take the real part of that. Now, if you see, there is some optimizer decorator here. This optimizer decorator, what it does is essentially it takes your optimizer and makes it work for pi trees. So if you remember for part 1, we said that there are these structures called pi trees. There are a list of lists, and then the basic structures of parameters in JAX. So this is how you save parameters, right? In this big list of dictionaries and all these kind of trees. Okay, so step 1, fix the atom optimizer to be complex atom, right? Again, we need to handle batches. So this is exactly the same code as it was before. We have this structure that we provide batches, and then it chooses the mini batches for us during training. And this is done again in this JAX kind of way, that we provide some initial key, and then they start splitting the key such that each time we get something different. Okay, so let's go and talk about stacks. All right, so if you remember, we talked about this stack serial. This stack serial library is essentially, it takes a lot of, you provide layers, right? And then we take this, it takes those layers that they are defined as pure functions and stacks them together as operations that they are done one after the other, serially, right? So in the Fourier neural operator, we have an initial lifting of the dimensions, right? And then iteratively, we need to do this nonlinearity, and then this WV, which is this transformation, plus the kernel, right? So we have a lot of things going on. And then we can take all those things, put them in stacks layers, and then stack them together such that we can apply all of them serially, like you see here, like a dense, and then this V iterative, iterative update, right? And then this is what we would like to do. Stack all this operation one after the other to make them act iteratively. Okay. Right. So as we said before, each of these functions will be defined by an initialization function and an apply function. Okay. So now we need to understand how we can define this pure function that you see here, dense, FNO, block2D, and all of the others, such that we can have this kind of structure. So whatever goes out of or the first one goes to the second one, and then goes to the third one, and so on and so forth. Okay, so let's start by talking about the dense layer. Oh, something that I forgot. Again, another property that we would like to have is that we would like to not care about the batch dimension, right? So we would like to have -1 here, which means that you will vectorize on the batch dimension. Okay. So let's go talk about the dense layer, which is a very simple implementation of a fully connected layer. So what do we have here? We have, again, an initialization function that is essentially creating the parameters, as we've seen in tutorial 1. And the other thing that we need is this apply function, which is essentially the forward pass, like it applies the transformation. Okay, this is the first thing that we need. The second thing that we need is a permutation layer. In the permutation layer, such that we permute the channel and the spatial dimensions, such that we apply the fast Fourier transform to the spatial dimensions, right? And then the permutation layer is again will be built in a stacks pure kind of manner. Okay, so if you see here in the initialization, we have two things. This provides us with two outputs. One will be the parameters. The other will be the output shape. So the output shape of the first layer will be the input shape to the second layer. The output shape of the second layer will be the input shape to the third layer, and so on and so forth. And this is how we will have this construction that stacks together layers serially, one after the other. So you need to be careful that when you have this this series of transformation, whatever is the output of one goes as the input to the other, the shapes, right? Because this input shape here that you will see in every initialization function, what it does is essentially that initialize the weights, right? So this provides you with the shape of the parameters. Okay, so this permute function does not have any weights. Now, this is the part that we started talking at the start, right? About the convolutions in the Fourier space, right? So what we have done here, we will define a spectrum convolution. Okay, so in order to do that, we will have, again, an initialization function. What is this initialization function? This initialization function will essentially be some complex matrices, right? If you read the paper, you will see that essentially in the 2D convolution, this 2D convolution, you need two matrices, right? That represents the two corners of this R matrix. So we will define two matrices, one W1 and one W2. And then this initialization function will provide us again with these two complex pi trees with parameters, so pi trees with complex parameters, and then an output shape. Okay, so the apply function we will perform the real fast Fourier transformation to the input, so the real fast Fourier transformation to V, and then it will perform these matrix multiplications with R, and then it will provide us the inverse real Fourier transform. Okay, so because there is some conjugate symmetry here, this is why you have the half of the domain. So don't be alarmed by that. All right. So the next thing that we need to do is add this part, this WVT. So we have computed out of this part here, we have computed this part, and now we compute this part, the WVT. So in order to compute the WVT, we will use a dense layer, the one that we have defined above. So what do we have here? We have a dense layer, we have and times the VT, and then what we have, the second one is this inverse of the Fourier transform that we have computed up here, right? So we created a new block, the FNO block, that will provide us with this exact thing. So this will be constructed by two parts. One that computes this, which is, we talked about that above, and one that will compute this. Again, we need an initialization function and an apply function. The initialization function will provide us with the parameters of this WV transformation, and the parameters of this Fourier, inverse Fourier, right? So the output shape now should be it's like what we discussed before. Now this output shape will be the input shape to the next layer that is stacked serially, right? And then at this point we essentially do this summation of these two parts, and this is the second thing that we want. Okay, with these three simple blocks, the dense, the permutation, and then FNO block to D, we will build the whole architecture, right? By stacking them one after the other. Next, let's talk about the loss function. The loss function is the same as it was before, right? In the Fourier neural operators, they're using, in their paper, they're using this loss function, which is, we call it relative L2 error loss, which is essentially a way, as we said before, this is a structured way to put weights in each loss function component. That's pretty much the idea, to avoid, overfitting at specific frequencies, something like that. Okay, so, and this is how we define it, right? As we did before. And now we go to the large model class. Okay, so if you remember, again, we need to define a layer, and this layer is a composition of layers, is a composition of transformations. A composition of transformations, the one that we talked about above. So these three transformations, dense, permutation, and FNO2 block to D, put them serially together to get one layer, that's a big layer one, which is a layer of serial transformation. Okay, and then again, this will provide us with a init function and an apply function. Again, we do this, we define it, we get the parameters, we do this unravel pi tree, because we take this pi tree, we unravel it, right? And then we will use that to store our parameters such that we don't need to retrain. Okay, and then we define again the optimizer, the complex Adam in the way that we talked about the real Adam optimizer, let's call it, which is, again, we need an initialization parameter, an update rule, an update function, initialization function, update function, and one function that will provide us with the parameters, right, the state of the influencer. Again, we have some loss. We have this L2 error such that we can compute the L2 error as we train, so that we see how well we do, right? And we have this step, right, this function, which is pretty much updates the state of the optimizer at its point in the training loop. And then we have the training loop, and then this function to count parameters, right? This is pretty much the idea. Okay, so again, we have these model definitions, and we have we load the data. We have some definitions here, how many, the number of input-output function pairs, the batch size, how many iterations we will train, and all that. So here we also compute the grid, right? And then, oh, something that I forgot. This R matrix, right? That with the matrix with the complex value parameters, right? So if you see here, we will create a grid, the input grid, like the spatial grid, which is the same as the output grid. And then we will concatenate it with the input function samples. And this is the input to our model. So one might think that in order to perform this Fourier trick, we said that the kernel is stationary and there is no connection to the input function, right? But now we are taking the input function in this R. So it's actually very interesting because the input functions now are like the R is parameterized with respect to the input function. They're not some argument. You can read it in the paper. This is very interesting. Anyway, so the other thing that we need to do is take our data, right, and make them like JAX device arrays, and then put them in the data generation to handle the batches. And this is how we define our model, right? Dense, permutation, blocks, activations, then permutation, again, one dense to lift the dimension even more, and then GELU, and then project it back to the dimension of your output. Okay, so this is how they define it in their paper, their code they have in GitHub. This is the way that we did it. So here we define the model, we count the parameters, and then we train the model. Okay, so if you see this trains in 6 minutes or 7 minutes, something like that, which is more than the DeepONet that trains in 1 minute, but it has some increased accuracy, it's like pretty 0.3% or something, right? And then what we do is essentially that we fetch the parameters, we do like a one-shot prediction for all realization for all the whole resolution, right? And then we compute the error, right? This is how we compute the error, and we will see the mean, the standard deviation, the minimum, and the maximum, right? And then the other thing that you can do is pretty much, save the model parameters such that you can use them for, don't train the next time. You can use them such that you don't need to train. So that's the end of the third tutorial. Yeah, thank you.
All right, I think we have a few minutes for questions, either on the method side or on the implementation side. It seems that everything was super clear.